So as we go through these problems, it strikes me that it's easier for you to follow along if you print these out before you listen to the video. So go to the Wild Courses site, find these files, print them out, and then you can follow along more easily. Okay, so in this problem, there's a spool. It's got a radius of 0.4 meters, an inner radius that the cord wraps around of 250 millimeters, and you're pulling with a force of 600 newtons. That's constant. So in this problem, they want to know what the angular acceleration of the spool is at this instant. And so it doesn't involve moving over a distance of length, which would be an energy problem. It doesn't involve a force being applied for a certain amount of seconds, which would be a momentum problem. So this is an equation of motion problem, an F equals ma problem. So the first thing to do to solve an equation of motion problem is to draw the free body diagram. And if you cannot draw the free body diagram correctly, you cannot solve these problems. So to draw a free body diagram, first you draw a closed loop like this. Then you draw everything that's in the loop, which I've done here. Okay, and in the loop, there's the weight, mg, going down. That's it. Then you draw everything the loop cuts through. So at the ground, where it contacts the ground, it cut through a normal force and a friction force F. It also cut through that rope there at a force of 600 newtons. Okay, on the other side, you just put ma, which is at the center of gravity, and I alpha, spinning around the center of gravity. And so then all you're going to do is use three equations, some fx, some fy, and some moment about some strategic point. And you can solve for the three unknowns that will be there after we take into account some other givens. So now I want to just stop and talk about these rolling problems. There's always two things that can happen. It's either not slipping, in which case if it's not slipping, you do not know what that friction force is. It is not mu times n. But what you do know, the additional information you do know, is that if it's not slipping at the bottom, it's not moving, so the acceleration at the center is r times alpha. So that's the additional information. So while we're at it, let's talk about the other possibility, and then we'll continue with the solution. In the other possibility, it could be slipping, which means then you do know the friction force. It is mu n, but then in that case, the acceleration of the center of the wheel is not r times alpha. So in the one case, no slip, you don't know the friction force, but you know the relationship between alpha and acceleration of the center of mass. If it is slipping, it's the other way around. You do know the friction force, mu times n, but you don't have a relationship between acceleration and r times alpha. So let's go through both solutions, and I'll show you how to check which one is true. So back to the no slip solution. Okay, so if it's not slipping, we know that a is r times alpha and the radius is 0.4 times alpha. And again, the reason for that, let me draw that here. That has zero acceleration because it's touching the ground, and that's spinning with alpha. This r times alpha is the acceleration of the center, because the distance from the bottom to the center is r. Okay, so that's the additional kinematic equation. So in this case, I'm going to take moments about the bottom, point O, right here at the bottom, because that will get rid of this unknown friction. Okay, so taking moments about the bottom, looking at that picture, you have 600, and the distance from the bottom to there, if you look at the picture, is 0.65 meters. So you have this here. That's the moment about the bottom of the left-hand side. And the moment about the bottom of the right-hand side, so I'm going to take moments about this bottom point right there, is I alpha. That's just a moment, right? So I alpha. And then it'll be m times a, but we just said that a is r alpha. So m times a, which is r alpha. So that's the acceleration. And the moment of that about the bottom, ma times this distance, which happens to also be r. So it's m r alpha times r. And if you factor out the alpha, it's just I plus mr squared. And those of you who are familiar with that, that happens to also be the moment of inertia about the bottom of the wheel. Okay, then we do the y direction. I'm taking up as positive, so n going up, mg coming down, and there's no y acceleration, so the normal force does equal the weight in this case because there's no y acceleration. And then finally, we'll take the x equation, right being positive, 600 going to the right on the rope, the friction force, which we don't know, going to the left, and m times a, but we know that a is our alpha. So what you do, you solve this first equation here. You can solve that for alpha. You know n, and then you come to this equation here and solve that for the friction force F. Now, how do you check if this is not slipping? It's not slipping if this friction force, which you just solved for, is less than mu static times the normal force, which you know is mg. And if that's true, you're done. If it's not true, then it is slipping, and you have to continue to this next solution. So if it's slipping, we now know that the friction force is mu n, but we don't know the relationship between alpha and a. The y equation isn't changed, so n is still mg. And so we immediately know, now that we know m, we can get the friction force, which is mu kinetic times n, because now it's sliding. So the other one, we're checking if it's starting to slide, so we use the bigger mu static. This one, we know it's sliding, so we're using the mu kinetic. So right away, you can get this friction force, mu times n. Okay, so in this case, since I do know the friction force, and I don't know the acceleration, I'm going to take moments about the center, where the acceleration goes through. Okay, so I'm trying to be clever about that. So let me scroll this down here so you can see the picture. So taking moments about the center, you have that 600 pulling on the rope, and its distance from the center was 0.25 meters. And then the friction force, which we now know, because it's mu times n, it's 0.4 meters from the center, and these are both going clockwise. And the reason I took the moment about the center is that MA goes right through there, so the only moment on the right-hand side is I alpha, and you can immediately solve for alpha. Next, we do the x component, and again, we know the friction force, so again, we have 600 going to the right. We have the friction force going to the left, which is just mu times n, we know that, equals ma. And so you can immediately also just solve that for a. And so now how do you tell if it's slipping? Well, you know it's slipping if you did the other one first, but what if you did this one first? Sorry about that, I'm having coughing fits here. So if it's slipping, what's happening, this is going faster than it's rolling, okay, because it's slipping. Turns out that you'll have the acceleration of the center not equal to r alpha. So it could be actually greater or less depending on if it's braking or accelerating. Okay, so if A is not r alpha, it's slipping.